I'm back with a chapter 16 applications video, so let's work a few temperature and heat problems. In this first problem, we see that we are in Palm Springs on a warm day. It's 113 degrees Fahrenheit, so I'm not sure that the word nice should be there. We are going to convert this temperature to Celsius and then again to Kelvin. So we're going to need a formula. Take a look at that formula chart. And you should end up choosing this one. And if you want to go ahead and pause this and try this on your own and then hit play again, that is perfectly fine too. So let's start writing down our information. We have 5/9, and that's degrees Celsius over degrees Fahrenheit. And then we're going to multiply this by our Fahrenheit temperature, which is 113, minus 32. When we do that, we'll find that our Fahrenheit temperatures cancel out, leaving us with 45 degrees Celsius. Okay, that's part A. Now let's go ahead and convert that to Kelvin. This is the really easy part. Remember, the Kelvin temperature is just the degrees Celsius temperature plus 273.15. And when we do this, we will find 45 plus 273.15 gives us 318.15, and that's Kelvin. But if we're doing sig figs, then we would just drop the decimal and it would just go to 318 Kelvin. And that is it for that problem. Problem number 2. This time we're going to think about something, and I'll draw a little image to help you. So it says we have rod 1, and we're just going to say rod 1 is here. And we have rod 2, and it says it is twice as long. So my second rod, and I'll use a different color for that. That's about twice as long. It'll work. So we know that when rod 1 is heated by some amount, it's going to increase in length by some amount delta L. We don't really know what that is. So I'm going to represent that with a brand new one. So this, after it's heated, is going to become a little bit longer. So here, this part can be my delta L. Well, if this second rod, the rod here, is twice as long, but it's made out of the same material and it's heated by the same amount, we want to know if its length is going to increase by delta L, 2 delta L, or delta L will be greater than 2. Okay, so let's think about this. And here is something that might be helpful to think about. So we know that delta L is equal to alpha, which is that coefficient, times the original length times delta T. So if this second rod is 2 times as long, then we know the expansion will be 2 times as much. So the only possible answer here is 2 delta L. So it'll increase by twice the length of this first rod. On this problem, we have a washer with a hole in the middle, and the washer is the metal object that is shaped kind of like a donut. So it looks like this. And then it has a small part in the middle. As the washer is heated, does the hole, so does this part, expand, shrink, or stay the same size? And then what is the best explanation? So if you think back to that lecture video when we talked about things that are flat and their expansion, I hope you remember that when something flat expands, everything expands. It isn't just this outer portion. It isn't just the whole portion. All parts of this expand. So if we considered the inner part of this as well, this would expand also. So with that being said, the only possible answer here is 2. Every dimension of this washer is going to expand. Okay, so that was it for this one. And again, this is for a flat object. Now, here we have something slightly more complicated, but that's okay. It's not much more complicated. So we have a copper flask with a volume of 201 centimeters cubed, and it's filled to the brim with olive oil. If we increase the temperature of that system from 11 to 36 degrees Celsius, how much oil will spill from the flask? Well, this would be important to know. So here is a very important piece of information. We are wanting to, if we want to know how much oil spills from the flask, then we need to figure out our change in volume. And looking back at that formula chart, there were two formulas that talk about the change in volume. But we are working with oil. Oil is not a solid. Oil is going to be considered a fluid. So we must use this equation to find our change in volume. All right, let's go ahead and find this information. Now, we have our volume. It's right here. And we have our temperature change. What we don't have is this beta value, but the beta value is something that is a constant, so we can easily just look that up. And when we look up this beta value, so I'll just go ahead and write it down for you. So you would be able to refer back to a table for this. It is, well, from the table, 0.68 times 10 to the negative third, and then that's the inverse Kelvin. Ooh, can't read that. Okay. Now, when we do the temperature, it's currently in degrees Celsius, but we want that to be in Kelvin. So let's go ahead and change degrees Celsius to Kelvin. Why do we need Kelvin? Because we have Kelvin here in this beta value. So 11 degrees Celsius to Kelvin, so that's just 11 plus approximately 273. So that'll be 284 Kelvin. And our ending temperature is 36 Kelvin. 36 degrees Celsius plus 273 Kelvin. Okay, so put the 6 here. Just do it like this. That's a 9, a 10. Okay, so we get 309 Kelvin. So if we find the difference from 309 to 84, we'll find that our change in temperature was 25 Kelvin. And we have our volume. It's 201 centimeters cubed. All right. Now that we have this, let's go ahead and calculate the volume change in the oil. Okay, so this is our first step. All right, let's put everything in. So we're going to take these three values and multiply them all together. And when you do, so again, you're multiplying the beta value, the delta T, and this volume. There's our V. Multiply those together, and you're going to get that the change in volume of the oil is about 3.4 centimeters cubed. Okay. So that tells us the change in volume of the oil, but it did not tell us how much oil would actually spill from the flask. From the flask. We need to know one more piece of information before we can solve this. This was the delta V of the oil, but we also need to know if there's going to be any change in volume for our copper flask. And to find the change in volume for a solid, we do not use this formula up here. Well, we use something very similar. It's going to be 3 times alpha, and this is the value for copper. And that's times V times delta T. Okay, so let's plug in our information. And again, we just get this alpha value from a table, and I'll go ahead and give it to you. This is 17 times 10 to the negative 6. And I didn't adjust these numbers. I'm just getting them from a table. Oh, and that's the inverse Kelvin. Okay, our temperature change is going to be the same, 25K. So we have alpha. We know our volume, which is also the same. And we know our delta T. So the only thing that changed was alpha, and it's multiplied by 3 now. So the delta V of the copper flask is about 0.26 centimeters cubed. So not a very big change. Okay. So if we want to know overall how much is going to spill, let's take the change in volume of the oil and then subtract the change in volume of the flask to get our overall change in volume. Oh, I'm sorry. That's 3.1 centimeters cubed. So this would be our final answer. That is how much oil would spill from this flask. Okay, let's go ahead and try the next one. Now, here, and this one might be a little bit more complicated to understand, but I'm going to do my best to explain it. So we have a farmhand who is lifting a bale of hay to some height, and this height is 1.1 meters. So he's lifting the hay here. They're going to put it into a truck. How many bales of hay could the farmhand lift using the energy provided by a 485 calorie milkshake? All right, so this is going to require us to think back to the relationship between heat and mechanical energy. And the first thing we want to do, so this is given to us in calories, but we need to get this in joules, which is a value for heat. So let's go ahead and convert 485 calories into heat. Now, here's something to make note of. This capital C calorie is not the same as a lowercase c calorie. So this capital C calorie is actually equal to 485,000 lower C calories. And we obviously use the capital C calories on our food boxes because this would be an absurd number of calories. Okay. Anyways, the conversion, you take a look at your formula chart. 1 calorie is equal to 4.186 joules. And so that equals 2.03 times 10 to the 6th joules. So here is our energy in joules. This is our Q value. Okay, that part's easy enough. Now, if you recall the picture from Joule's experiment, and maybe you do, maybe you don't, there was a mass that fell some distance, and the work that was done on that mass was done by gravity. So our mechanical work here is going to be similar. And our mechanical work will be equal to mgh because we have a bale of hay being lifted into the air. And we're going to say capital H because that is how it is denoted up here. And this is going to be our equivalent for heat. So Q is going to equal mgh. Now, we were asked to figure out how many bales of hay, but I don't see any variable in here that indicates bales of hay. So don't forget, they're moving multiple bales of hay, and each one is having this amount of work done to it. So we're going to say Q equals N, and we're just using N as a random letter. I guess we could just use, actually, why am I using an N? We'll just use a B to represent bales. Okay, there we go. Multiplied by mg times h. So now this is the hardest part, was figuring out this formula. Now that we have that, we can just rearrange and then solve for B, bales of hay. So the bales of hay is going to be equal to our Q value divided by mgh. Let's plug in everything we know. 2.03 times 10 to the 6th joules divided by, and that's 23.5 kilograms, 9.81 meters per second squared, and 1.1 meter. Okay. Work this out, and you should get a value of 8,000. So this would be 8,000 bales. So using the calories from this one milkshake, this farmhand could theoretically lift 8,000 bales of hay into that truck bed, which is an absurd amount. So this milkshake has a lot of energy within the calories in there. Okay. Next problem. This time we are looking at a block of metal, and we see that it has an initial temperature of 54.5 degrees Celsius. And it's dropped into a container that has about 1.1 kilograms of water, and that water has a temperature as well. If the final temperature of the system is 21.4 degrees Celsius, we want to know the specific heat of that metal block. And then knowing the specific heat will allow us to identify the block, though we don't have to do that here. We're going to ignore the container and assume that it is perfectly keeping all of the heat inside of the container. Okay. So here's what it looks like after. It starts at the temperature of the water and the temperature of this block, and it ends all at the same temperature. So that's going to be very important. And here is the equation we would want to use for this. The specific heat, C, is equal to Q divided by M delta T, also known as Q equals MCAT. Okay, sorry, just wanted to write that. So let's see what we have here. We need a value for Q, and we need a value for, no, we have a value for M. And we have a value for delta T. So the only thing we seem to be missing here is Q. So take a moment and see if you can figure out where we would get Q from. All right, so maybe you figured this one out and maybe you are completely stuck. So here is how we will proceed. We know that whatever amount of heat is lost by one object must be gained by the other because the heat is trapped in this container, so it shouldn't be able to escape. We're assuming that it doesn't escape. So that means that our Q's will just be equal but opposite. So one of them is going to be positive and one of them will be negative. Well, let's see which one that would be. So the one, well, okay, Q equals MC delta T. So I just rearranged this. I've rearranged this equation. And we can go ahead and replace the Q's with the equation. Okay, so all I did was take my Q and I put MC delta T instead of Q. Again, one of these is absorbing heat and the other is releasing it. So the one that is absorbing the heat is the substance that increases in temperature, and the one that is releasing the heat is the one that decreases in temperature. So my water is going from 20 degrees Celsius to 21.4, which means it increased in heat, so it absorbed. So we're going to say this side is the positive, this side is the negative. That means this is my side for water, and over here on the right, I have my side for the metal. Okay, well, I have 1.1 kilograms of water. C is just the specific heat, which we can look up from a table, and it is 4186 joules per kilogram Kelvin. And my delta T is 21.4 minus 20, because delta T is final temperature minus initial temperature. We're going to set that equal to negative. Let's see, the block, here's the mass of the block, 0.50 kg. We do not know our C value for the block. That's what we want to know. And the delta T is the final temperature is 21.4 because at the end, the block and the water are the same temperature. And the initial temperature is 54.5. And we can leave degrees Celsius here. That is not a big deal. And it's not a big deal because they're going to end up canceling each other out anyways. Okay, so we do this side over here for the water, and you should get 6446.44 as the value. And we would set that equal to what we got on the other side, which we have a negative here, and this value is going to end up being negative as well. So that will go away, and we will end up with a positive. So we're just going to end up with 0.5 multiplied by, and I have my calculator here. So 21.4 minus 54.5. That would be 33.1 times 0.5. Okay, so this would be equals 16.55 C. So then let's just divide 6446.44 divided by 16.55, and we'll find that our C value is about 390 joules per kilogram Kelvin. So this would be our final answer. This is our specific heat of the metal. Okay. Here we have another concept question, so this one will be fairly fast. We're looking down here at this image, these images. We have this side and we have this side. So on the left, we see we have two rods, and they're both shorter. Well, they're the same size, but in this first picture, we see the rods are parallel to each other. And in this second picture, we see the rods are beside each other. They're touching. We want to know if the heat conducted in this left arrangement, in the parallel arrangement, is greater than, less than, or the same as the heat conducted over here in the right arrangement when everything is in a series. All right, so let's consider a couple of things. When we want to know how much heat is conducted, so this has to do with conduction, something we talked about towards the end of the last video, then we have to consider the cross-sectional area. That's one of the things we have to consider. We also have to consider our temperature difference across, from one end of the rod to the other. Well, let's start with area. We know each of these rods is the same size. So the area here is going to be the same as the area here. However, when we are looking at this one on the left, we would have two areas that we got to take into account. Whereas over here in this one, we only have one, because we're just going to treat this rod like a whole. So that's our first point. So this section has a larger area. Second, we have delta T. We see it's going from 0 to 100 both times in both cases. Here on the right, we have this rod going from 0 to 100 and this rod going from 0 to 100. So that's twice the temperature difference. Over here, we just have everything in a row, so we see a temperature difference occurring once. So we're going to find that a lot more heat is conducted over here in this parallel arrangement. And our best explanation for that is here. It is because the area through which the heat flows is much greater. Okay. Now, we're going to take something very similar to what we were just looking at. We're still looking at rods. This time, we're going to talk about a lead rod and one that is copper. They are connected in parallel, and we see the temperature difference is 2 to 106. They have a square cross section instead of a circular one. And that cross section is from here to here, 1.50 centimeters. And it would be the same on this side because it says it's a square. So how much heat will flow through those two rods in 1 second? All right. So go ahead and take a look at your formula chart. And I'm going to put the formula up here. You should use pause this if you don't want to see it yet. This is the formula we will be working with today. Now, since we have two different substances, we're going to need to do this twice. We're going to need to do this one time for lead. Oh, you can't even read that. I'm so sorry. And we're going to do it another time for copper. Let's start with the lead. Remember that these K values, these can just be looked up. That's not a big deal. And when we look up that K value for lead, we're going to find that it's equal to 34.3, and that's watts per meter Kelvin. Now we need the area. Well, they told us the side length, but we don't have an area, but y'all know how to find area. Area would just be length times width here. So 1.50 times 1.50 would give us the correct value. But notice this is in centimeters. We see that our constant K already has a unit of meters, so let's just go ahead and convert centimeters to meters. That won't be a big deal either. So that would go to 0.0150 meters. And we're going to square that since it's area. 0.0150. And that's squared. And then we have our delta T. So our change in temperature, 106 to 2 degrees Celsius, that's a change of 104, divided by the length of our rod. It says it's 0.525 meters. And finally, we're going to multiply that by time, which in this case is just 1. So that's 1 second. So my QLE, lead, still can't read that, is 1.53 joules. Let's do the same thing for copper. We look up that value and it's 395, so that's much larger, watts per meter Kelvin. And our area is the same. This is squared. Temperature difference is the same. And the rods are the same. Finally, the time is the same. So everything was the same except this original beginning value. When we do this, we're going to get 17.6 joules. We wanted to know the total heat that would flow through the two rods. So all the heat, and all we have to do there is add this value and this value together. So 1.53 plus 17.6 joules equals 19.1 joules. And this is our final value. So this is how much heat would flow through those two rods. And the last problem. Okay. So I'm just going to kind of read you this problem. We have some humans who are going to go swimming into very cold waters. We have the surface area of the person and the surface temperature of the person. We want to find the net radiated power from this person in a dressing room where the temperature is about 20 degrees Celsius, and outside where the temperature is around 0 degrees Celsius. And here is the emissivity that we will be assuming. So if we're looking for net radiated power, go ahead and find that equation. I'm going to put it up here. It looks like this. So we need to solve for P, and I will do part A, and then y'all are going to do part B. So for part A, power equals, okay, here's the emissivity. That is this letter here. Well, this variable here, and it gave it to us. It's 0.900. That means this person's pretty decent at radiating heat. And then we need our value here now. I hope y'all remember what this is. It's that constant. Here it is. Boltzmann's constant. And it is 5.67 times 10 to the negative 8 watts per meter squared Kelvin to the fourth. That is a crazy unit, I know. Finally, not finally, sorry. We need the area, and we were told an area up here, so we can just plug that in, 1.15, and that's meters squared. Finally, we need the temperature, and here is where we're going to have to do a little something. So this is temperature to the fourth. We need to know we need to know the temperatures, and we have them in both Kelvin and Celsius. So you've been given two different temperatures. We see a surface temperature, which is right here, but we also have the temperature outside. So we're going to take our temperature, the surface temperature, and subtract the temperature of the space that this person is in. So the surface temperature of the human minus this temperature is going to give us our T to the power of 4. And I like to do it this way. I'm just going to do it times because I'm running out of room. I'm going to do it like this. So this will be 303 Kelvin, and I'm going to do this to the fourth power, put brackets, minus this temperature, which is 293 Kelvin to the fourth. And I chose to use the Kelvin temperature here because this unit of Kelvin is present and it won't cancel out otherwise. So when we do this math, you should find 62.1 watts. Okay, that was the power that would be radiated in part A. So now y'all are going to do the same thing for part B and press play when you're ready. Okay, so the answer for part B, I'm only going to give you the final answer because it's just like the one we did before. It's 169 watts. So here's part A, 62.1 watts and 169 watts. So we see that in this cold environment, this person is radiating a significant amount of heat compared to when the person is in a room temperature environment. That brings us to the end of the applications video. Please let me know if you have any questions, and thank y'all for watching.